Epic. Epic! Epic Stat Tool 1 Speedruns of Statistics! Brian Stevens! Versus Chapter 12 From Randomness to Probability. Begin!
When it comes to formal probability, there are rules for probabilities. The first rule is that probabilities have to be between 0 and 1, and this can include 0 and 1. So what does this mean right here? Well, the lowest possible probability is going to be a probability of 0. I think about the probability of meeting Deadpool. Now, it'd be awesome to meet Deadpool, but it's not going to happen, which means the probability of it is 0. Now, what about the probability that the sun will come up tomorrow? Because the sun is going to come up tomorrow. At least I would say that has a 100% probability, and that means it will happen. So probabilities are between 0 and 1, inclusive, 0 being the lowest probability, meaning it can never, will never happen, and 1 being the highest probability, meaning it must happen. So that's what we're talking about when we say probabilities are contained between 0 and 1, and that's what it means when a probability is at 0 or 1. So when do we have invalid probabilities? Well, an important thing to know with invalid probabilities is something like when your parents tell you to give 110%. So we talk about when you play a baseball game or something and your parents tell you, a probability like give 110%, so put in here baseball. So with baseball, if your parents say to you, give 110% of your effort, well, this right here would be an invalid probability. This is a probability that is outside the bounds of 0 and 1. You can't give 110%. Not possible, because that is a probability or an amount outside of 0 and 1. Now, also, when it comes to probabilities, we'd have the set of all probabilities has to add up to 1. So if you think about an example like a color wheel, where we might have just 2 colors on the wheel, maybe we have red and we have orange. So if we have 2 colors right here, red and orange, so there's our orange and there's our red. If we put probability of red right here, probability of red is going to be 50%, and the probability of orange is going to be 50% also. And what you'll notice here about the sum of all these probabilities is that they add up to 1. So when you look at the sum of all probabilities, they must add up to 1 for disjoint events. You can't, on this wheel, spin orange and red, so we have disjoint events. More on that to come. Now, the law of large numbers. What is the law of large numbers? The law of large numbers is going to be what we expect to see in the long run. So let's take, for example, a coin flip. When you think about a coin flip, you can flip a coin. Let's just write down here a coin and think about flipping it here for a moment. So we have a coin that can come up either heads or a coin that can come up tails. If you were to go here and graph what happens as you flip the coin flip, going from one flip, or put one flip right here at the beginning, that makes sense to put 0, then one flip right here, and then 2, and then 3, and then 4, and then 5, and 6, and 7, 8, and 9, and 10. When you flip this coin, what would you see? Well, on the first flip, you might have a percentage of heads that is 100%. So the probability of heads right here, put right here, right sideways, always hard to do. The probability of heads is now at 100%. And what happens in the long run is you might see the next coin flip is also heads. Well, then the next one is going to maybe be tails, and we have 2/3 now. And then the next one is maybe heads, and we have right here a little bit more, and maybe a little bit less, and a little bit less, and a little bit more. And it's going to slowly move to what are we going to see in the long run eventually here? What would we eventually see in the long run? Well, in the long run, we're going to see this approach 50%. In the long run, we're going to see a 50% probability as this goes to the long run. So the law of large numbers states that in the long run of trials, we'll observe the true probability of an event. So think about with just one coin flip, you're either going to see 100% heads or 100% tails, and this coin is not going to start to show the true probability of heads, which is 50%, till we start to flip it in the long run, till many long trials. And this is the law of large numbers right here, showing us that with the long run of trials, we will see the true probability of an event. Now, this is different than the law of averages, which states that this coin is due to flip tails because it just flipped tails, heads, and heads. So you can't say, okay, it is going to flip tails here on this trial right here because it just flipped heads and heads. That is the law of averages. The law of averages is a fallacy, and fallacies are things that we cannot trust. So let's say you're playing hands of cards, and if you're playing a hands of cards and you keep getting bad hands of cards, so let's go down here to a new page, and you keep getting really bad cards. You're getting 2-7 repeatedly in poker, and this is a really bad hand. You just keep getting it. So you might say after you keep getting bad hands of poker that you're due for a win. But think about this. These cards right here, they don't care that you've been losing. These cards are not sentient. At least we don't think so. So these cards don't give you better hands because you've been getting bad hands. Each hand is independent of the previous one. So when you get your next hand, the probability of it being 2-7 or the probability of it being pocket aces are the exact same no matter what your previous hand is. So it's not going to influence the next hand. But you will see in the long run that you'll get maybe pocket aces the percent of time you would expect. But pocket aces are not more likely because you got bad hands previously. To once again state it again so we can remember, the law of averages states, which is a fallacy, that you'd be more likely to get pocket aces from getting bad hands in the past. That's a fallacy. The law of averages says in the long run you would observe the true probability of this event. So if you kept playing more and more hands, you would get this on average as long as you would about what you would expect. So we do need to remember what the law of large numbers is, and then we do need to remember the law of averages is a fallacy version of it where people think past events can predict what will happen for independent future events. Now, what does it mean for something to be disjoint or mutually exclusive? Now, these are topics that people often confuse because disjoint and mutually exclusive are the exact same thing. So let's use a green pen right here to denote that these are the exact same concept. Disjoint and mutually exclusive mean the same thing. And I always like drawing it out this way right here. If we're going to think what disjoint and mutually exclusive means, think about two rings like this or two rings like this. Now, when we talk about things that are disjoint, in version 1 of this right here, the first version, we have that they are disjoint. And in version 2, they have a jointed area. You'll notice right here, there is an area where they connect. So version 2 is not disjoint. And what does this mean? Well, let's just write here the probability of getting a dog is this one right here. So we'll put probability dog, and then we'll put right here probability cat. So with this one being the probability of a cat, this means you can only get a cat or a dog. There is no instance where someone gets a cat and a dog. Now we have here the probability of dog for this one. So here's the probability of dog, and here's the probability of cat. And what does it mean that they're not disjoint? So this is not disjoint. Let's write that below here. So the one on the right is not disjoint. So this is not disjoint. And the one up top on the left is disjoint. So if getting animals is a disjoint event, you can either get a dog or you can get a cat. You can't get both. You could technically get neither, which would satisfy being disjoint events. But if they're not disjoint events on the right, you can get a dog and you can get a cat. There is an overlap when both things can occur. So this is not disjoint right here. And think about what mutually exclusive means. If we say things are mutually exclusive, that would mean they exclude each other. So the one on the left is also what we would say is mutually exclusive. So mutually exclusive. And the one on the right is not mutually exclusive. So when you think about things being exclusive of each other, they are not going to include. So the mutually exclusive means that there is no inclusive part between these. They exclude each other. This would not be mutually exclusive right here on the right. So when you think about events that are disjoint or mutually exclusive, they would be when both things cannot occur. You can only get a dog or you can only get a cat. You can't get both. What does it mean when two things are independent of each other? Well, independent is a key term we should know and we've already talked about. Independent is going to be when knowing one event tells you nothing about another. So what does an example for this look like? Well, let's look at independent events as an example here. With independent events, imagine you know it's raining today. Now, would this tell you anything about how you're going to do on your statistics exam? So the probability of rain is 80%, and the probability of making an A on your exam is going to be something like, let's say, 30%. Pretty good probability right there. I'll take it. So the probability of making an A is 30%. Now, knowing that it's going to rain, would that tell you anything about you making an A? No. But what if we change this right here to events that are dependent? This is an example of independent events right here. So if we go to dependent events, let's change this to the probability of snow. And here it is. The probability of snow today is, let's say, 80%, because it's maybe we live in the north and it's middle of December, so there's a high probability of snow. But today, let's say we know that the probability of it being above 32 degrees, so greater than 32 degrees, is this right here. So if you know it's above 32 degrees, like let's say it's above 32 degrees outside, would that change the probability of snow? In this way, the probability of snow is dependent on the temperature. So the probability of snow here, if we knew it's above 32 degrees, which is unlikely, we live, let's say, in Vermont or somewhere. So with this knowledge that it's above 32 degrees, that would change the probability of snow, because the probability of snow is going to be dependent on the temperature. So we would see a change to the probability. So always ask yourself this: I know it's above 32 degrees. Does that change the probability of snow? And if it does, then you have dependent events. Or go back to our previous example where you say, I know it's raining outside. Does that change the probability of me making an A on the exam? And you'd say, well, with the knowledge that it's raining, that does nothing to the probability of me making an A, i.e., these are independent. So that's your real test right there to say, I know it's raining outside. Does that do anything to the probability of me making an A? The answer is no. Then they're independent. They do not influence each other. So next we have the concept of know that disjoint events are never independent and independent events are never disjoint. Well, what does this mean? Well, let's go back to our disjoint example. So when we have disjoint events right here, like the cat-dog example right here, what does it mean that these disjoint events are not independent? Well, it means that these are dependent. So write this down here. Let's write it down above it. Is that disjoint events are very dependent. This is a great note to have, that disjoint events are very, very dependent. And let's explain what that means in context of this example. If somebody in this disjoint example right here were to get a dog, if they were to get a dog, you would know that they didn't get a cat. And just think about that. What we just talked about a moment ago in independent means if things are independent, they give you no information. But knowing someone gets a dog means the probability of cat is now what? The probability of cat is now 0 because they can't get a cat if they get a dog in disjoint events. So when you have disjoint events, they are very, very dependent, because if one event happens, the other event can what? Cannot happen. So disjoint events, when one happens, the other can't happen, and that means they are dependent. Now, independence and disjoint are different topics, but it is true that they have an overlap, that disjoint events are very dependent. Think about grades in a course. Grades in a course are going to be disjoint events. So when we have grades in a course, you would have something like, you could either make an A, B, C, D, F, and let's look right here. And just think about this by filling in the circles. As soon as you know somebody made a B in the course, you've answered all the other questions, because you can't in one semester make an A, a C, and a D in a course. You only get one grade in the course. So by knowing which disjoint event occurs, the other disjoint events cannot happen. Even if you say somebody in a class has a 20% probability of making an A, well, now this 20% probability has gone to 0 because you know they made a B. With the knowledge they made a B, you now know they can't make an A. So this is what we mean by saying disjoint events are very, very dependent of each other. And dependent is the same as not independent. Next, we have understand the multiplication rule and the necessary conditions for using this rule. Let's draw out a really, really great table right here. So we have the multiplication rule, and we also have the addition rule right here. So the multiplication rule and the addition rule, I like to draw on a table. So let's draw that table. For this table, we need to draw the rule. So let's go right here. And we have here the rule. And we have the sign. And we have the word. And we have the condition. Okay. So the two main rules we need to remember are the multiplication rule and the addition rule. The sign for multiplication is multiply. I think it's pretty obvious right there. Addition is add. The word for multiplication is and the word for addition is or. And the condition is going to be independent right here, which we've already talked about a little bit. And the other one is disjoint. So let's make sure to have this written down. This reads right here, the rule is multiplication, the sign is multiply, the word is and the condition is independent. We have the rule addition, we have the sign adding together, we have the word or, and the condition is disjoint. So let's take a look at some examples of this and see how it works. The addition rule is going to be the simpler one to do, and let's use grades in a course. When you go back to the grades in the course example, we've got different probabilities right here, and we acknowledge that all of these are disjoint, as in they can't occur together. You either make an A or a B, you can't make both. And there we go using the or word right here. So if the probability of an A is 20%, let's go right here and go probability of making an A is 20%, probability of making a B is 30%, probability of making a C is 30%, and we're at 80% right now. Probability of making a D is 15%, and the probability of making an F right here is 5%. Don't make an F. So with this right here, we should have 100%, and we satisfy the rule that the sum of all probabilities is equal to 1. A little bit of review right there. But take a look. What do we get if we say, what is the probability you make an A or a B? So making an A or a B means we just add together these two probabilities. That's all we need to do right here. When we talk about making an A or a B, we have disjoint events, and we can add them together. Make sure you satisfy the condition that these are disjoint events to add them together, and we can just simply add together what's the probability you make an A or a B, and this is 50% right here. So the probability of making an A or a B, the probability of these two right here is 50%. Now, I do want to mention this. We do sometimes write trick questions because what's the probability of making an A and a B? That would be 0. You can't make an A and a B because they are disjoint events. So watch out for trick questions like that where you're like, wait a minute, these are, disjoint events right here. I can't make an A and a B. That would be multiplying them together, and that would not meet the rule of independence. So to multiply two things together, we're saying they both happen at the same time. That's what the multiplication rule is implying, that you have this occurring and this occurring right here. Two things occur at the same time, and we're going to say this happens and this happens. So let's say we have two teams that are playing completely different games. And historically, so we have the Patriots and we have the Browns. So we have the probability of win for the Patriots. We'll go probability win team 1 and the probability of win team 2. Now, they're not playing each other because then it would be dependent. So we have two different teams, two different games, and the first team tonight, historically and due to the odds, is going to have a 60% chance of winning their game, and then the other team has a 50% chance of winning their game. Now, one team winning will not influence the other team. They're playing two totally different teams. So what is the probability that team 1 wins and team 2 wins? All we're going to do right here is multiply these two events together and get this right here. We're going to get 30%. And this would be the probability of team 1 winning and team 2 winning. Notice the key word right here is and. So team 1 wins and team 2 wins. And there's the probability that they both win their games tonight. Now, what's the probability that at least one team loses? Now, would you agree with me that we will either have the instance of both will win, team 1 will win, team 2 will win, or both will lose? This is the set of all possible outcomes. So when you think about this, we just found out the probability right here that both teams win. So the probability that both teams win is 30%. That means if you look at all of this right here as a set, we have the probability of 70%. So we're actually doing a very complex problem here to figure out the probability that at least one team loses. And you can see it right here by looking at the complement rule, which is just 1 minus the probability of the event we're looking at. And it's also a bit on the addition rule. But take a look. We have either that both teams win or at least one team loses. And mathematically, what we would do here is we would just do 1 minus the probability both win. And we have the mathematics shown on the screen right here. And this would be probability at least one loss. So at least one loss. at least one lost. There we go. Just barely on the screen. So the 1 minus probability of both winning is the probability that we have at least one loser, and we are solving for that right here. And there it is. There is the mathematics we get down here. So it's a bit of a complex problem where we have to solve for at least one. One of the classic ways we do this is with a coin flip. So let's take a look at a coin flip problem. When we do at least one right here, we could talk about a coin flip where we have tails or heads, and the probability of either is going to be 50%. So what is the probability of getting at least one heads when we flip a coin 5 times? So would you agree with me? There are the instances that we get 0 heads, 1 heads, 2 heads, 3 heads, 4 heads, or 5 heads. Like that's how many heads we could get. We could get 0, 1, 2, 3, 4, or 5 when we flip a coin. Such as like, think of this instance where we flip coins and you have something where this is heads and this is heads. So you got 2 heads. So hard to see my small drawings right there. So let's use colors instead. So we have the instance right here where we have this one and this one are both heads. So there were 2 heads. We'd fall into this instance right here. Or we have an instance where we have 3 heads, and it could be any sort of arrangement of this, where it could be these 3. There's many, many ways this could occur. But there's only one instance where we get 0 heads, and that's this one up here, where they're all tails. So either, would you agree, that they'll be all tails? So let's draw right here this. So we have all tails right here. Or there'll be at least 1 heads. Either there'll be all tails or there'll be at least 1 heads. So what do we have? Well, mathematically speaking, we have here that this is going to be some value x, and this is going to be some value y. And listen to the or word right here. Either we have all tails or we have at least 1 heads. So with all tails or at least 1 heads, since one of these must occur, the sum of all probabilities is equal up to 1. And look at what we have. We're trying to solve for this over here on the other side, that there's at least 1 heads. So when we solve for this over here, we're actually solving for y. So we're interested in this, and all we need to do is just change around the mathematics a little bit to do 1 minus x, or y equals 1 minus x. So y is equal to 1 minus x. When we solve out the mathematics right here, we just subtract x from the other side. So x is all tails. So let's plug in right here all tails. And all tails is going to be 0.5. And we just say we get tails and we get tails and we get tails and we get tails. So that's going to be 0.5 times 0.5 times 0.5 times 0.5, because we're saying this happens and this happens and this happens and this happens and this happens. And that would be raised to the 5th. So all we're doing is multiplying this out up here up top by saying we get tails and we get tails and we get tails and we get tails. And here is the mathematics right here, and this would be the probability over here. So that is how we'd solve it in at least one problem. These are pretty tricky. They're the hardest part of this chapter maybe, but do a bit of review, and there's some great homework problems over that. So understand the complement rule and be able to apply it. That is exactly what we're doing right here with the complement rule. Either A occurs or not A occurs, and we've just done some complicated problems with that right here. State whether or not it'd be reasonable to assume a set of events is independent or disjoint. Once again, reviewing the terms right here, independent and disjoint. Independent means if something is independent, knowing A tells us nothing about B. So 2 independent events would be something like you wake up early and your favorite team wins their game tonight. You waking up early would tell you nothing about your team winning the game tonight. So they're independent events. But you wake up early and you get to class on time. Well, if you wake up early, you might be more likely to get to class on time. Those would be dependent events. Now, when we think about disjoint, once again, disjoint events are very, very dependent. Disjoint means if one happens, the other cannot happen. Review those parts of the video. We're right under 24 minutes. Great job. You know, we always challenge people. Let's challenge Cheese. Cheese is doing those Mario 64 runs, just acing them. With that, great speed run. Practice up.